Good morning and welcome to the Great Lakes Legislative Caucus webinar focusing on nuclear waste in the Great Lakes region. This is the first of two webinars on this topic. Both webinars are part of the caucus's Great Lakes Great Webinars series for 2014. I'm Lisa Hanairo with the Council of State Governments Midwestern Office. I staff the caucus and am managing the logistics for this webinar. We'll start with a few housekeeping items. First, this webinar is being recorded. The slides from the presentations and the recording will be posted on the caucus's website this afternoon at the address you see on the screen. You'll receive a follow-up message with a link to the recording and also the address where you can find both the recording and the slides. To reduce the possibility of feedback or other external noise, while the presentations are running, the conference will be in listen-only mode. After each presentation, we'll open up the line for questions. We want this webinar to be interactive, so if you do have a question, please let us know either by typing your question in the GoToWebinar Questions pane or by clicking on the hand icon to raise your hand. If I see that your hand is raised, I'll unmute your line so that you can ask your question. If you accidentally click on the button to raise your hand, just click it again and it'll turn off. Next, a few tips if you do plan to ask a question. If you're using your telephone, please make sure to enter your audio PIN, which you'll find in the audio pane. If you selected Voice over IP and you're using your computer's microphone and speakers, please test your settings by clicking on the Test Settings link in the audio pane. Your connection to the webinar audience will be muted, so don't worry about anyone hearing you as you test your microphone. If your computer's microphone doesn't appear to be working, you should call in using one of the telephone numbers listed in the audio pane and make sure to enter your PIN. And finally, after the webinar, you'll all be asked to take a very brief survey, just 3 questions. Please take the time to fill out the survey so that we can get feedback to help us improve our webinars. I'll now turn the floor over to the chair of the caucus, Minnesota Senator Ann Rest.
Thank you, Lisa, and good morning to everyone. Our Great Lakes Great Webinar series for 2014 continues today with a webinar that addresses nuclear waste in the Great Lakes region. As legislators, we often focus on issues directly related to water quality, such as our last webinar on Asian carp. But an emerging issue for legislators is the indefinite, very long-term storage of nuclear waste from power plants near the shores of the Great Lakes. This waste is the product of generating electricity from nuclear power, so those of us living in states with nuclear power plants are ultimately responsible for its creation because we use the electricity. Currently, the federal government in the United States assures us that the material is stored safely, but storage is temporary. What we all are expecting is a permanent solution that will protect future generations and the environment, including our Great Lakes. The speakers on today's webinar will help us understand where the waste is located, what the future plans are for it, and what states and provinces can do to help ensure that the Great Lakes are being protected adequately from incidents or accidents involving nuclear waste. We are very pleased to have 3 speakers with us this morning. Our first speaker will be Kevin Powers, who is the Director of Public Affairs at Ontario Power Generation, or OPG. Kevin has worked for OPG for 3 years. Prior to his work at OPG, he spent 6 years as the head of communication at Ontario's Ministry of Energy. Prior to that, he worked abroad as a public affairs consultant and started his career as a reporter with the Associated Press. Kevin will be joined in his presentation by Mark Jensen, who is the Director of Deep Geologic Repository Geoscience and Research at the Nuclear Waste Management Organization. From 2002 to the present, Mark has directed geoscience studies related to the environmental assessment and regulatory licensing of the proposed Deep Geologic Repository, or DGR, for low and intermediate level radioactive waste. Kevin and Mark will share with us information on that proposed facility, which would be located in Kincardine, Ontario, near Lake Huron. They'll also update us on the status of the licensing process for the facility. Our third speaker is David Strack, from the U.S. Nuclear Regulatory Commission. David is a Senior Project Manager in the Division of Spent Fuel Storage and Transportation. He has over 22 years' experience with radioactive material packaging and transportation, including 14 years' experience with packaging, transporting, and storing spent nuclear fuel. David will talk to us about the storage of spent fuel at nuclear power plants in the U.S. and about the status of the licensing process for the Yucca Mountain Repository, whose future, or for that matter, whose present, is mired in uncertainty. I thank all of our speakers for joining us this morning and will now turn the floor over to Kevin Powers.
Good morning, and thank you for the opportunity here to speak about our proposal to safely and permanently bury Ontario's low-level and mid-level nuclear waste in stable and ancient rock formations so it will never pose a threat to people, the environment, or the Great Lakes. Over the next 20 minutes, I'd like to provide you with an understanding of the project, the science behind the project, and the regulatory approvals in place to ensure that the project will only be built if there is shown to be no adverse environmental effect beyond a reasonable doubt. By way of background, we work for Ontario Power Generation. We are Ontario's largest producer of power. We have approximately 10,000 employees, and we are owned wholly by the province of Ontario. Our assets include 65 hydro dams, which you see on the picture here as blue dots, as well as the ownership of 3 nuclear power plants. The Darlington and Pickering nuclear power plants located on the shores of Lake Ontario, and the Bruce nuclear plant located on the shores of Lake Huron. And the Bruce plant there on Lake Huron will be the focus of our attention here today. By way of background, nuclear energy produces 50% of the power in Ontario and has done so for 40 years. Though nuclear does not produce any greenhouse gas emissions, it does produce waste, which we classify into 3 categories. There is high-level waste, which is used fuel and which is not under discussion today. The proposal we have today is for intermediate-level waste, which is resins and filters from the filtration system of the nuclear power plants, and low-level waste, which includes industrial items such as mops, gloves, etc., that you would find in any manufacturing setting, but because it takes place in a nuclear plant, is stored separately from regular waste. Now, low and intermediate level waste has been shipped safely for more than 40 years from all of our facilities to the Bruce nuclear facility on Lake Huron. Here I have a picture of part of the Bruce nuclear site. The Bruce nuclear site is the largest nuclear facility in the world. It has 8 reactors. And what you see here in the bottom right corner, labeled 1, 2, 3, 4, is where the waste is currently stored in warehouse facilities and buried partly underground. Our proposal would be to move that waste 100 yards away to the area labeled number 5 and bury it 680 meters or 2,230 feet underground. That 100-yard move has taken us since 2001, and we are not there yet. In 2001, the community of Kincardine, where the waste is currently stored and which houses the Bruce nuclear plant, came to us and said that they would be interested in permanently storing the nuclear waste that currently resides there, but they wanted a safer and more permanent solution if they were to do so. From then, we began feasibility studies and an assessment study which looked at 3 options for the burial of the nuclear waste. Kincardine Council selected the Deep Geologic Repository as the safest and most permanent solution. It held a resolution, and we signed a hosting agreement, and the hosting agreement was only valid if we would conduct a community poll and get acceptance from the entire community. That poll was held, and 60% of the population said yes, that they would be willing to host the facility. That began 6 further years of study into all aspects of the project, and it culminated in a 12,500-page report that concluded that this would have no impact on the environment or the lake. That proposal and that report was submitted to the Joint Review Panel, which is, and as I will explain a little later, the most rigorous form of environmental assessment in Canada. That was submitted in 2011. In 2013, we held 5 weeks of hearings into the project, and I will talk about that a bit later. On the next slide, you'll see a schematic of the project. You'll see here that on your right-hand side, we have the CN Tower, which gives you an idea of how deep this will be. For our colleagues in the U.S., that is the equivalent of 4 Washington monuments deep. It is 680. It would be stored 680 meters below ground, and the closest point to the lake would be 1.2 kilometers. The project would be located in stable, low permeable rocks with multiple natural barriers to isolate and contain the waste. And to talk a little bit more about that, I will pass the presentation over to Mark Jensen, who will talk a bit more about the rocks and the safety case. Mark.
Good morning. Thank you, Kevin. I'd just like to speak a little bit now about the geology and the safety of the repository as we now know it from our investigations over the past decade. At a glance, this slide kind of shows the main elements of the DGR, the proposed DGR. Just to get your bearings, in that lower left you can see an aerial photograph looking north of the Bruce power development, where there's 8 reactors, and then its location on the eastern shore of Lake Huron, 10 kilometers north of the town of Kincardine. What we know from our investigations at present is that the site rests on a thickness, layer cake sequence of sedimentary rock that's 840 meters in thickness. And in that sequence, there are 34 bedrock formations. The bedrock formations are very old geologically. They're from the Paleozoic period, and the ages are around 390 to 540 million years old at the base of that sequence. The key issue with regards to these sediments is that they contaminant migration within these low permeability sediments is diffusion dominated, and what that means is that any contaminants released would migrate at a rate of less than 1 millimeter per year, or a meter over 1,000 years. So this is a preferred type of environment for radioactive waste management or any long-term waste management purpose. The repository itself, you can see it here, it consists of 2 panels and 31 rooms. I'll discuss that in a second. But it was purposely positioned within the Coburg Formation. It's a 27-meter thick limestone formation, mechanically strong, extremely low permeability at a depth of 680 meters beneath the site. It was also selected because above that horizon there is 200 meters of shale, equally low permeability, and that provides the barrier between the repository and surface and groundwater resources. The repository itself would be accessed by 2 shafts. They are islanded, which means they're very close together. The shafts would be concrete lined on construction, the main shaft being 6.5 meters in diameter and the vent shaft being 5 meters in diameter. At closest approach, the main shaft is 1 kilometer from the lake, about 3/4 of a mile. And the waste at its closest point is about just a little bit more than that at the depth of the closest emplacement room that you can see in the panel here. In terms of the process, what we're going through in terms of the environmental assessment is for a construction and site preparation license. Looking forward, what would occur is, if granted through the environmental assessment and licensing process, construction would take place, and once that began, it would take 5 to 7 years to construct the entire facility, the shafts, the work service area, and the panels themselves. Then we would have to apply for an operating license to allow us to actually put waste into the facility. If that license was granted, the facility would work for 35 years, during which there would be 200,000 cubic meters of low and intermediate level waste in placed. At the end of waste and placement, you would again submit for a license to decommission, at which time, if granted, the shafts would be sealed and the system would be passively safe, and there would be no need for intervention. The wastes would be safe, secure, and isolated from the environment. So I'll just speak a little bit more about the geology of the site. Kevin, I can't seem to advance the slides.
Yes, this is Lisa. I'm sorry, I'm unable to turn the controls over. Kevin will have to advance the slides. My apologies.
This slide represents the regional geology. It's a little bit larger scale. You can see the main elements, the Michigan and the Appalachian Basin. To get your bearings again, the blue dot represents the Bruce nuclear site. And the feature that we're dealing with is called the Michigan Basin, which takes up the left-hand side of the figure. It's large and it's old. In width, it's approximately 600 kilometers in width. Its deepest point is beneath the A in Michigan, where it's more than 4.8 kilometers or 3 miles in thickness. But on the eastern flank, where the Bruce site is, those sediments are thinner, as I've said, around 840 meters in thickness. So if we can move to the next slide, please. This slide provides a cross-section, so a vertical section through that layer cake rock stratigraphy, and you can see where that cross-section is in the lower left-hand corner with that red line. And what we can see here is on the right-hand side, you can see Ontario, and you can see where it says DGR2. That's the location of the Bruce site and the proposed DGR. You can see Lake Huron, you can see Michigan, and Lake Michigan to the far left. What's key about this really is that the sediments are fairly undeformed and have large lateral extent. They are flat-lying. In fact, at the site, they dip at about 10 meters per kilometer, which is about 2 inches over 30 feet, which is virtually flat. And the other key thing is that because of this, this property, this lateral extent, we do have experience in some of these formations elsewhere in southern Ontario. And that gives us a kind of a view of what conditions underground might look like. So if we could have the next slide, please. Just click one more time. So what we have here is, can you go back, please? Yes. What we have here is a map of the geology, the sedimentary geology within southwestern Ontario. And that rose-colored dot represents the location of the Darlington Nuclear Generating Station, where a number of underground excavations were created in the Coburg Formation, where it occurs near surface. And here you can see a figure, a photograph of that excavation 30 meters below Lake Ontario, extending out about 1 kilometer, and it was dry and mechanically stable. This is the type of condition that we would expect to find at the repository level beneath the Bruce site. One click, please. Here you can see the Queenston Shale, and this is the distinctive red-colored unit that is in the cross sections. It is 80 meters in thickness. It represents 40 meters of the 200-meter thick shale barrier above the repository. And here you can see a test at it that was created in the Niagara Falls region. It's 13 meters in diameter, being excavated by a roadheader. But the important point is that these shales are extremely low permeability, they're thick, and they're massive barriers to contaminant transport and provide for the isolation of the repository itself. One click, please. And here you can see the dot on the Bruce site, and this is the example of what conditions might look like at a depth of around 40 meters beneath the site. At this depth, we know we have fresh groundwater aquifers in carbonate rocks that extend down to a depth of around 160 meters, very permeable, very wet, and this is the sort of condition that we're avoiding by using the shafts to go down to 680 meters, because once you get down below 160 meters at the site, the conditions are essentially dry. Next slide, please. This is the understanding of the geology. It's sort of a cartoon, but it captures all the main important elements of the site and the reasons why we would like to pursue this proposal. Horizontally, it covers 100 miles, that cross-section. The pink at the bottom represents the Precambrian Canadian shield rocks on which these sediments were laid. You can see in the gray, the red, that's the Queenston Shale, and the yellow-colored rocks, those are the sedimentary rocks. You can see the location of Bruce site on the eastern shore of Lake Huron. You can see the location of the repository in the Coburg Formation beneath the red and the gray shales that's there. You can also see Lake Huron, and you can see there's a line just below the triangle, the upside-down triangle on Lake Huron that represents the deepest depth to which Lake Huron is excavated by past glacial erosion. And what is important here is that we know that the deepest parts of Lake Huron do not intersect or have not compromised the barrier integrity of these shale units that blanket the repository and provide for safety. The key thing here in this was that we divided this in the early days in 2002 into 3 groundwater systems that you can see almost in the center. One is the freshwater system, fairly permeable, and it's used in the vicinity for livestock and other rural purposes. Then we have an intermediate level aquifer in which the permeabilities of the rock and the age of the rock gets older, and the quality of the water is decreased. It gets saline, where the water is 300 grams per liter, seawater is 30 grams per liter, and acceptable rates is about 0.2 grams per liter. So the water down there is ancient and undrinkable and usable. And then the lowermost unit, 400 meters from the top of the red to the top of the pink, represents that 400 meters of what we call Ordovician age, or 450 million year old rock. And it consists of an upper 200 meters of shale, 200 meters of limestones below that. And the hydraulic conductivities or permeabilities of these rocks are some of the lowest that have ever been measured in any radioactive waste management program. Next slide, please. So based on that understanding, back in 2005 when we designed the site characterization studies for this, we came up with these what we call favorable geologic site features. And these were hypotheses or questions that we posed to the group that was going out to do the work to collect data to confirm these. And in a sense, by confirming these, it kind of gave us confidence that the site was suitable for purpose. So the first was that it was predictable that we had bedrock units that were horizontally layered and of large lateral extent. Second, there were multiple barriers. We weren't relying on one bedrock formation, but multiple bedrock formations in combination to create a level of redundancy in the barriers. Also, that the contaminant transport was diffusion dominated, which I mentioned as being the best situation for long-term waste management. The natural resource potential was low. This included shale gas, base minerals, and salt. Seismically quiet, so that we did not have to worry about strong ground motions. That it was geomechanically stable, that we could create the openings without any cave, and that they would be virtually dry. And most important, the shallow groundwater resources and the Great Lakes were isolated for all times and safe. Next slide, please. We didn't do this alone. We had teamwork. There was over 30 groups working on this at any one time, looking at unique aspects of it. In particular, there was technical oversight from the French and Swiss programs who have worked in sedimentary rocks for more than 2 decades for radioactive waste management. So that was independent oversight. We had a number of specialist groups. We did have groups working that had developed methods, for instance, at the waste isolation pilot plant during its licensing and deep borehole testing, that we welcomed their participation in this work. There were also a large number of universities that participated in a wide range of areas of geoscience at trying to understand the stability and evolution of the system and most importantly, groundwater motion and migration. A couple of American universities were involved from Washington, looking at things like glacial erosion, which we have to be concerned about at this site that was glaciated 9 times in the last million years. 22,000 years, it had almost 2 miles of ice on top of it. So a large number of people contributed to this, and the documents were created and submitted in April of 2011. They've been publicly available ever since, and we would welcome any questions on those documents. Next slide, please. One more click. This is just a quick slide to kind of give you a potpourri of the activities that were conducted between the fall of 2006 and really the summer of 2010. We conducted the site characterization in 3 phases, drilling phases. We drilled 6 deep boreholes around the footprint of this repository so that we had it within, we had a perimeter around the footprint. Each of these boreholes was cored, so we had a physical record of what we intersected. And here you can see what the results of that was in terms of the geologic attributes. These attributes link into the original hypothesis. We know that it's thick. We know that we have multiple bedrock formations. The groundwater system is ancient and stable. In fact, we believe the water contained within the pores at the repository depth were there at the time that the sediments were laid in those ancient oceans. There is good reason to believe it's geomechanically stable, as I've shown you from the photographs elsewhere from excavations in these formations. Natural resource potential and seismic hazard are low, and that contaminant transport is diffusion dominated and has remained so despite glaciation and other mountain building events that these sediments have been subjected to. Last slide, please. What we do with the geology is that another part of it is to look at long-term safety and look at different scenarios that take into account how we think the site is going to evolve with time, how it might evolve based on our uncertainty in certain parameters or distributions of parameters, and eventualities for the site. And you can see the flow diagram looking here, the repository at the bottom colored red, and the different pathways in which radionuclides could in the future be released. These analyses contribute to calculations of what potential outcomes might be at surface, and in this particular case, it was considered to be a farm-dwelling family living directly above the sealed shafts. And the lower graph kind of provides a histogram of those occurrences, and essentially what has been done is that background levels shown on the far right are around 2 millisieverts per year. That's what you would receive just by living and having normal medical procedures. The agreed to rate for this project is 0.3, to almost 20 times less. And then you can see how the different bars represent from the different scenarios what the dose rates could be in the future. And these are all 100,000 times less than the regulatory criterion. In that gray shaded area, they are virtually zero. And it's very important to note that these impacts occur at times beyond 1 million years. This system is so isolating that any sorts of events that we can calculate that look to be virtually zero are in the far future. With that, I'd like to turn it back to Kevin to complete. Thank you.
Thank you, Mark. Over the course of our studies, we have worked, as Mark noted, with a number of many scientists from around the world, and we have submitted our data to various organizations. I have here a couple of the organizations that we have submitted that to. The U.S. Environmental Protection Agency has reviewed our submission and provided comments. They have said that in comparison to other international programs, our DGR is the deepest planned facility in the world, is bounded by the thickest assemblage of low permeable cap rocks, and is isolated from surface and drinking water. The Department of Environmental Quality in Lansing, Michigan said that in summary, they have reviewed our environmental impact statement and supporting radiological and geologic studies and have no technical objections to the conclusions reached in the many various studies. As I noted, we submitted the environmental impact statement, the 12,500 pages, in April of 2011. It was submitted to the most rigorous form of environmental assessment available in Canada, which is called a joint review panel. In February of 2012, the Joint Review Panel opened up all of the information to the public for 4 months of comments. That turned to 16 months of comments, which ended in May 2013, and resulted in 575 questions that OPG was asked to answer. As I noted, we had 25 days of hearings over the fall of last year with 300 interveners, and it was one of the longest hearings in Canadian history. The Joint Review Panel is continuing its detailed review of the information on the record, and the public registry will remain open until all of its information requests have been answered and that it is convinced it has sufficient information to close the record. Once that is done, participants will be allowed final submissions, and the Joint Review Panel will prepare reports which will be submitted to the Federal Minister of Environment, who will have 120 days to make a final decision. And that decision is expected in 2015. With that, I will wrap it up and open the floor to any questions.
Thank you, Kevin. This is Lisa Hanairo. We have just about a minute for a question. If anybody has one, either raise your hand or type it in the questions pane. I do have one. Kevin and Mark, I assume you're familiar with the waste isolation pilot plant in New Mexico?
Yes.
And I've heard that the Bruce Power facility is described as being similar to WIP. There was a radiation event at WIP on February 14th, and the Department of Energy is still trying to figure out what happened there. Do you anticipate that this event will have any impact on your own licensing process? That is, might it extend the process a little longer so that you can incorporate whatever lessons learned are going to come from DOE's investigation of what happened at WIP?
We don't know that it will extend the period of the hearing, but we are, of course, closely monitoring the findings there, and will incorporate any of the findings from the WIP facility into our planned facility.
Okay. I don't see any questions in the queue right now, so I'm going to turn it over to David Strack for his presentation. And Kevin and Mark, you're welcome to stay on the line. David?
Yes, I'm here. Give me 1 second to pull this up. All right. Senator Rest, I thank you for your earlier introduction. I am David Strack, a Senior Project Manager in the Division of Spent Fuel Storage and Transportation at the U.S. Nuclear Regulatory Commission. I'll present to you today information related to storage of spent nuclear fuel in the United States and the status of our Yucca Mountain review. Here are the topics I will be covering. I will speak about 3 separate but related topics associated with spent nuclear fuel. After an overview of spent nuclear fuel storage and extended storage, I will present information that is specific to the current storage of spent fuel around the Great Lakes. Lastly, I will provide an overview of the Yucca Mountain project and highlight some of the current activities that the NRC is engaged in on that topic. Let me open by reminding you that the U.S. Nuclear Regulatory Commission was established in 1975 as a result of the 1974 Energy Reorganization Act, which divided the existing Atomic Energy Commission into the Nuclear Regulatory Commission and the U.S. Department of Energy. The NRC's mission is to license and regulate the civilian use of radioactive materials in the United States, to protect the public health and safety, to promote the common defense and security, and to protect the environment. Within all of that, we have 2 primary goals, and they are safety and security. I'm calling you today from our headquarters in Rockville, Maryland. We do have 4 regional offices of the NRC across the United States. They are in King of Prussia, Pennsylvania, Atlanta, Georgia, Lisle, Illinois, and Fort Worth, Texas. We have about 4,000 employees who are devoted to the safety and security and the use of and storage and transportation of nuclear materials. Let me begin by showing a map that indicates the current location of the 54 operating independent spent fuel storage installations in the United States. If you notice in the key in the lower left-hand corner, it does indicate those 54 operating facilities. As well, we have inklings from at least 11 other facility or other sites that are considering their options for and getting into the business of storing spent nuclear fuel on their sites. You can access this map at your leisure. Below the key is what is called the ML number. That number can be utilized in our Adams document management system, which is available through our website. And you'll see the website in the very last slide that I have. Just in general terms, the spent fuel pools at the reactors cannot maintain all of the fuel from the nuclear power plant, especially for those reactors that continue to operate and will operate for many more years. Thus, industry has developed dry cask storage of the spent nuclear fuel. In general terms, the storage of spent nuclear fuel is done in large steel canisters and concrete casks designed to be placed outdoors on reinforced concrete pads at power reactor sites or other approved locations on what is called an independent spent fuel storage installation. The acronym is ISFSI, or ISFSI. The two technologies currently being utilized include a vertical cask system, as seen on the left in this slide, and a horizontal storage module system, as seen on the right, in which a canister is positioned inside a concrete-walled, above-ground bunker, and that bunker is about the size of a single-car garage. Generally, the spent fuel must be stored and cooled in a spent fuel pool for a minimum of 5 years before it is placed into a dry storage canister. Once the spent fuel has cooled, the fuel assemblies are loaded into the canister, which is designed either for pressurized water reactor fuel or boiling water reactor fuel. Currently in the United States, as I mentioned, we have 54 operating independent spent fuel installations, and later in my presentation I will talk about the active 11 independent spent fuel storage installations that are located along Lake Michigan, Lake Erie, and Lake Ontario. Dry cask storage is a safe, simple, and reliable system that seals the used fuel into large airtight canisters that provide structural strength and radiation shielding. As I mentioned a moment ago, the casks are stored outside on concrete pads. These pads are generally 2 to 3 feet thick of concrete, and they can be very, very large. 100 feet by 200 feet is not uncommon at all for that particular pad. A pad that is that large would require nearly 500 truckloads of concrete and over 20 miles of rebar. The rebar in the left-hand photo, just for point of fact, is 1.25 inches in diameter, so it's very, very industrial strength rebar, if you will. In the right-hand photo, the wooden forms for the concrete are visible, and these would be in place during the pouring process for the concrete. Typically, the foundation under the pad is specifically engineered and may include a bed of compressed engineered fill, several feet thick, that provides a foundation that also acts as a shock absorber in the event of a seismic activity. Once placed in storage, the cask will remain on the ISFSI pad until a national repository is made available or other storage scenarios become available. Currently, the Department of Energy has proposed consolidated interim storage of spent nuclear fuel. Thus, this could lead to long-term storage of the spent fuel at the reactor site and until such time as a consolidation facility is available. Here's an example of a vertical dry cask storage system positioned on an ISFSI pad. Overall, there are just a few spent fuel canister vendors, each of which has their own unique design and specialized technologies for storage of spent fuel. In general terms, the storage casks are very robust. They are 18 to 20 feet high, generally 11 feet across, and some of them employ thick concrete walled overpacks. Those walls may be as thick as 2 feet thick of concrete, while others use just metal walls. When loaded with fuel, these systems are very heavy, reaching weights up to about 360,000 pounds each. You just saw the vertical system. Here's an example of a horizontal storage module, independent spent fuel storage installation. On the left is a typical HSM, or horizontal storage module, with the access doors removed. On the right is a similar HSM, again with the doors in place. Both the vertical and the horizontal storage systems are passive systems, meaning that there are no moving parts or operating motors or fans of any type. There are ventilation openings along the bottom and top edge of the systems that allow for natural convection and heat removal. Over time, the heat dissipates and the convection or flow of air decreases. Here is, again, an HSM. On the left, you see the walled bunkers with the metal doors in place. Also in that left-hand photo, you see a transport vehicle that is loaded with the cask with the spent fuel inside of it. And in the right-hand photo, that cask would be positioned using a transit, as you see in that surveyor's transit, as you see in the right-hand photo. And once the door is off and all the alignment has taken place, the fuel cask is pushed using a hydraulic ram that is part of that transport vehicle into that void space in the HSM. Here are two examples of what we call dual-purpose casks. This means that these casks have met the regulatory requirements to qualify as a storage cask under our 10 CFR Part 72 NRC regulations, as well as a transportation cask under our 10 CFR Part 71 regulations. Note the various components of the cask system, including if you look at the left-hand model, including the canister, which is in the blue, the fuel basket, which is in the green, and the covers that go over top, and those are in yellow. Similar components are also visible in the right-hand model. The concept of dual-purpose casks is important, especially when talking about extended storage of spent fuel and future options for final disposition of the spent fuel. During transportation of spent fuel casks, such as those represented in this slide, additional components, such as impact limiters or transportation overpacks, would be needed. The photo on the left here shows a typical spent fuel canister with the fuel assembly basket positioned inside of the canister. The basket is a series of square holes in which the fuel assemblies are loaded. The photo on the right shows a canister with a basket inside, and this one has been lowered into the spent fuel pool, so this photo is actually looking down at the cask, and the cask is positioned underwater. The photo also shows a fuel assembly being lifted by a crane and lowered into the spent fuel basket. And in this slide on the left, we see a large overhead crane for maneuvering the empty canister and eventually the loaded canister with the spent fuel inside of it. Once loaded, the canister is lifted out of the pool and drained. It is vacuum dried and backfilled with an inert gas, such as helium, which also serves to dissipate heat. The loaded canister is eventually welded closed by use of a computer-controlled welding machine, as you see in the right photo. Multiple passes are made over the weld, and those welds are performed in accordance with national welding codes and standards. Once the canister is leak tested, it is either moved to a storage cask for movement to a pad-type ISFSI, or it is moved to a transportation cask for movement into a horizontal storage module-type ISFSI. At the NRC, the Nuclear Regulatory Commission, it is the Division of Spent Fuel Storage and Transportation that has the responsibility for issuing the license for the spent fuel dry cask storage systems. There are about 68 staff who do the detailed technical reviews of the systems in areas of licensing and certification, as well as performing inspections and the quality assurance approvals. Areas that are analyzed during the overall approval include criticality, shielding, thermal, structural, and materials compatibility. These reviews are very complex and they can take many months to complete. Moving now beyond the overall topic of dry cask storage and now looking at extended storage, it is apparent that until a geologic repository is available, the spent fuel has to be maintained somewhere, and it must be maintained for some extended period. Thus, the idea of extended storage comes into play. The current policy for disposition of spent fuel is in transition, and extended storage may be necessary. It is the policy of the United States to dispose of the spent fuel in a permanent geologic repository. We don't have a repository here in the U.S., so we're kind of filling in that time, if you will, by using this extended storage technology. It is possible in the future that additional disposal options may emerge. These might use different type of geologic settings, or they might even use smaller packages for disposal. No matter what the policy environment is, the NRC remains committed to its mission and safety and security goals. There are several technical issues that arise when we consider regulating spent fuel and extended storage. The NRC needs to ensure the safety of the storage canisters and the overpacks, as well as to determine the safety aspects of transporting the stored fuel at some time in the future. To this end, the NRC has engaged on several research projects focused on these technical issues. We also are looking at considering revisions to our regulatory framework. I mentioned this just a moment ago. Part 71 for transportation and Part 72 for storage. There are different requirements for each of those areas of the regulations. The idea here would be to mesh those two ideas together, long-term storage and then eventual transportation. Extended storage of spent fuel can be done safely and through licensing renewals and routine oversight. During extended storage, licensees must develop aging management plans that identify potential aging effects. Once again, looking at this stuff over long term, we want to ensure that the material is being stored safely. Here at the NRC, we are finalizing the last few the technical information needs affecting potential regulation of extended storage and transportation, commonly known as the TIN report. That report includes the various technical areas that we are looking at, and we have engaged with national labs and the Center for Nuclear Waste Regulatory Analysis to look at potential degradation phenomena during the dry storage, overall extended storage of the dry cask systems. Areas that we're looking at, we've identified from a high priority down to a low priority, and I'll just cover one of these just in consideration of time. The first one that is listed there, stress corrosion cracking of stainless steel canisters and welds. Stress corrosion cracking is seen in environments where there are three ingredients. That is the presence of some type of salt, a fairly constant temperature coming off of, in our case, coming off of the storage cask itself, and a high humidity. This phenomenon we have identified in other stainless steel systems, and it initially begins as pitting of the stainless steel, followed by eventual cracking. During the manufacturing process of the canisters, flat 1-inch thick steel plates are rolled to form a right cylinder, and then the two edges of that rolled cylinder are welded together to make the complete circle. Both of these activities add stress to the stainless steel, and really this is at the microscopic level. So this is one area that we are looking at because stainless steel is a very common material that is used in the canisters during the storage process. We are also looking at and following the Department of Energy's efforts for a monitored cask demonstration project. In this, they would get approval from the NRC to put certain monitoring devices on a cask loaded with fuel, and we would monitor gas production, temperature, various other components associated with long-term storage, and compare that with what our actual regulations and what our safety analyses include. Make sure that we have essentially a one-for-one exchange of information that we're gaining and what our regulations are bounding. Moving forward now, I'll talk just very, very quickly about storage of nuclear fuel in ISFSIs along the Great Lakes. I will start my discussion with the Lake Michigan. And the first plant would be the Big Rock Point plant. They currently have 8 casks on their ISFSI, a total of 441 fuel assemblies. They loaded fuel during November 2002 through May 2003. If you notice in the first bullet there is one, it says 7/1, 7 casks of spent fuel, and they do have 1 cask with what is called greater than Class C waste. Greater than Class C waste means that it is not spent fuel, but it is material that would not qualify for disposal in a low-level disposal site because of the concentration of radionuclides. That's really beyond the scope of this discussion. But again, just the point that there are 8 casks at the ISFSI at Big Rock Point. At the Palisades Power Plant in Covert, Michigan, they use 3 dry cask storage systems. They have a total of 42 casks on their site with a total of 1,096 fuel assemblies. At the Donald C. Cook plant, they currently have 12 casks with 384 assemblies. Their particular ISFSI pad can hold a total of 94 casks. Within each of these slides, I list the slide vendor, and you can go to their website. I'm not promoting them. I don't have any connection to them, but if you want interest as to what their individual technology, their specialty that I spoke of a little bit earlier in passing, you could certainly do that. At the Zion plant, they have 6 casks with 222 assemblies. They began loading just at the end of last year. Point Beach, they use 2 different systems, and they have 16 of the VSC-24 system and 23 of the New Homes 32 PT system. At the Kewanee plant, they currently have 8 casks with 256 assemblies. They plan to load 6 additional casks in 2014. And as well, they are looking to transition and use a different cask technology, which they intend to deploy in 2016. The Perry plant along Lake Erie has 6 casks with 408 assemblies. Their pad is a very large pad as well, and it has room for 80 storage casks. At the Davis-Besse plant, they have 3 casks, 72 assemblies. They completed loading in the late 1990s. And at 9 Mile Point along Lake Ontario, they currently have 16 casks. Their horizontal storage module, they have room for 80 horizontal storage modules on their site. At the Fitzpatrick plant, also along Lake Ontario, they have 21 casks, just over 1,400 assemblies, and they loaded their last assemblies or last casks in 2013. And then along Lake Ontario as well is the Gannett plant. They have 6 casks with 192 assemblies. They also use a horizontal storage module. They have 10 of those in place. They have room for 30. I'm getting close on time here. The next topic that I want to talk about is Yucca Mountain. And rather than giving you a history lesson with a pop quiz at the end, let me just cut to the chase of our current activities as of 2014. Our NRC Commission has directed staff to complete the safety evaluation report for Yucca Mountain. We have staff who are engaged in doing that as we speak. They are currently on schedule to complete that safety evaluation report review by January of 2015. They have loaded the various documents known as the Licensing Support Network into our Adams document management system, and we are, again, moving forward with that Yucca Mountain review. Once we complete our review, that is just one step and several more steps that need to take place. But again, we are making headway with what we have been directed by our commission to do. Just in a quick summary, we do have 54 operating ISFSIs within the United States right now. We expect at least another 11 over the next several years. We are engaged with the various federal labs in looking at extended storage and technical issues that we have with those. We do have 11 operating ISFCs that are located along the shores of 3 of the Great Lakes, and we are moving forward with our Yucca Mountain Safety Evaluation Report. Information available about these topics or other items associated with our NRC activities are available at our website. And I'll turn this over now to Lisa. Thank you.
Well, this is Senator Rest, and I do want to thank you, David, for your very informative presentation, as well as Kevin and Mark. Lisa, do we have time for a question, or do we need to wrap it up?
Well, I think we have time for one question from the audience. I did have a question for David while people are thinking. David, you showed the slide with the sites around the Great Lakes. Last summer I had the opportunity to visit the Zion plant and also La Crosse, Senator Rest, over on the Mississippi River on the western part of Wisconsin. And I know the DOE team that I was traveling with headed up to Big Rock Point in Michigan. My question is, DOE has considered shipping spent fuel from those plants and also from Kewaunee and Point Beach in Wisconsin by barge, both on the Great Lakes and then over on the Mississippi River. David, can you comment just briefly on whether barge shipments of spent fuel pose any particular problems, such as specifically the recovery of a cask in the event of an accident? You mentioned how heavy the casks are.
Certainly the weight comes into play. As we approve these casks, we are different from the Department of Transportation. Our cask systems that we approve are not mode specific, so they could really go by any mode of transportation. Here in the United States, I'm not aware that we have shipped spent nuclear fuel by barge, but we have shipped other types of heavy components. As many as 100 of those have taken place here since the late 1990s. Steam generators, large components coming out of decommissioned reactors that weigh upwards of 1,000 tons each have been very successfully transported by barge and by heavy haul multi-wheel vehicles as well in combination with the barge. There would probably be a lot more political concern than scientific concern with transporting by barge.
Okay, thank you for that. And then quickly, the safety evaluation report for Yucca Mountain. Can you comment on why it's taking so long to complete that document, David? Is it resources or some other consideration?
Well, I'm not sure what is meant by taking so long. It's been on hold since 2008. We have not had any action on it at all. Again, if I had 3 more minutes, 5 more minutes, whatever it takes might have been to go through the complete history lesson, that would have been one of the comments. But we have been engaged on this really since January. We have staff that are dedicated to this. We have funds. $11 million was still available to do the review. We are required to give reports to Congress every month as to the status of the review, as well as the spending of the money, and all systems are go toward the issuance of that safety evaluation report in January of 2015. Okay. So we were on hold for quite a while. We're actively engaged. We're making good progress.
Okay, great. Thank you. And on the webinar in 2 weeks, we'll hear more from a speaker about bipartisan efforts to try to move forward with some solution for the U.S. Okay, thank you, David. Senator Rest, I'll turn it back to you.
Well, thank you, Lisa, and thank you to all 3 of our speakers, Kevin, Mark, and David, for your contributions to our webinar series. We've learned a lot today. And thank you to all the participants for joining us as well. And before we close, I just have a few announcements. First, we have one additional webinar planned before our 2014 annual meeting. That webinar is part 2 of nuclear waste in the Great Lakes region, which will take place at the same time 2 weeks from today on Friday, April 25th. We'll hear about Canada's search for a site for disposing of that nation's highly radioactive waste from nuclear power plants, and also about bipartisan efforts in the U.S. to develop a path forward for disposing of our own spent nuclear fuel. If you haven't already registered for the April 25th webinar, please visit the link you see on the screen, which is case sensitive, or visit the GLLC website. You'll find recordings and presentation slides from past webinars also on our website. If you participated in our February webinar on Asian carp, you may have heard that caucus members had an opportunity to sign on to a letter commenting on the U.S. Army Corps of Engineers draft report regarding Glimmerus. I'm pleased that we had 30 caucus members sign on to the letter, which we have submitted for the record on March 31st. A copy of that letter is available on the caucus's website as well. If any caucus members have suggestions for other advocacy efforts that can be undertaken by the caucus as a whole or by individual members, please pass your ideas on to Lisa Hanaro of the caucus staff. I want to remind the legislators on the line that if you aren't yet a member of the caucus, you may enroll by visiting the caucus's website or the online enrollment link shown on this slide. Membership is at no cost and is open to all legislators from the 8 U.S. states and 2 Canadian provinces in the Great Lakes region. One of the benefits of membership is that you may be eligible to receive a travel scholarship to help defray the cost of attending the caucus's annual meetings, which leads me to my final announcement. The 2014 annual meeting is 3 months away. The meeting will take place in Quebec City on July 24th, 25th, and our host will be the National Assembly of Quebec. To learn more about the meeting and to register, visit the caucus's website. Anyone wishing to attend should register by June 30th, which is the deadline for registering and for reserving a room at the Delta Quebec Hotel. We have a few travel scholarships available specifically for caucus members from Indiana, New York, and Pennsylvania. I look forward to seeing a large turnout in Quebec this summer. And now back to Lisa.
Thank you, Senator Rest. Remember to watch for a follow-up message with information on where to find the slides and the recording from today's webinar. And please take a minute to fill out the short survey that'll pop up as soon as we're done here. I hope you'll join us again in 2 weeks for part 2 of this series on nuclear waste in the Great Lakes region. And I also encourage you to tell your colleagues about the caucus's webinars so they'll know about this convenient and cost-effective resource for learning about and staying up to date on issues that affect the Great Lakes. This concludes our webinar. Enjoy the rest of your day and have a great weekend, everyone.